Hi. The purpose of this video is to essentially showcase the image alignment program that I built within Qupath. More specifically, I'm going to be using some of the open slide images, which you can see over here. And we'll be going through just a standard image alignment protocol from start to finish, including creation of the project itself, loading the images in, calculating the transformation matrix, and finally applying and writing out the aligned and concatenated image. Since there are several functionalities within this alignment script that allow for some manual alignments, optimization of alignment parameters, and several other settings, I'll try and go in depth, to the most common features used, but there might be some that I may end up omitting. In any sense, let's get started and we'll see how this goes. So I just want to make sure we're recording. Yeah, perfect. So first thing we want to do is to actually create a project. We'll create a new folder and call this image alignment. We'll copy the path of this folder and we'll paste it into this Qupath project. Create a project, paste path, select folder, and now we have our Qupath project with no images loaded in. Now the images that I'm going to be using are OS1 and OS2 and OS3 from the Hamamatsu and DPI OpenSlide test images or test data. Now what's interesting to note is that even though OS3 is labeled as NDPI, the download will end up downloading a TIFF file. But the great thing about this image alignment program is that whether you're working with NDPIs, SVSs, TIFFs, whatever, as long as you're able to get it into Qupath, you'll be able to align the image, to a reasonable extent. Again, it depends on the quality of tissue morphology, signal to noise ratio of your stain of interest, and several other parameters. So yeah, we'll give this a shot, but by no means is this guaranteed to work for any range of images. Yeah, so we've created our project. And the first thing we want to do is actually load in these images we've downloaded, specifically OS2 and OS3.ndpi. I'm going to skip out using OS1 because it doesn't seem to be a serial section. So, we can't really align those images. Anyways, set image type. We'll leave this blank for now because we don't really know if they're bright field, HTAB until we take a look. And rotate image. So I can't stress the importance of this enough. Do not rotate the image on import. Even if the images are actually rotated while you're loading them in, the script has a way of taking into account image rotations when it comes to performing the alignment. If you do include a rotation when you're importing the image, you're almost certainly going to encounter errors when you try to write it out. And this is an open issue within Qupath. But yeah, just no rotation. And yeah, you can generate the pyramids if you want, sure. So we're importing them now. And perfect, we have our two images. So let's take a quick look at them. This seems to be an HTAB image, and we'll have to name it according to the nomenclature delineated over here. Now, first thing we want to figure out is what stain this is. So OS3 is P10. So we'll name this OS3, OS3 underscore PTN. And we will change this to .ndpi. Now, the reason why we're changing the extension of the project file, but not the image itself, is because we need to have all files in the project list to have the same ending extension. Changing this does not change the image format. It's saved in as memory as a TIFF. I just need it to say explicitly .ndpi. Or we can change them all to .tiff, or we can change them to all .xyz. Doesn't really matter as long as the contents following the period is the same across all the images you plan to align. And we'll repeat the same here. So this is HDAB. We'll rename it. And we'll set it to, I guess we do have to change it to a 3. ki67.ndpi. So let's take a look at the naming of these files, which is arguably one of the most important parts of the image alignment. The set of the block, I guess you could say, of which the sections came from, all has to be consistent. So in this case, it's OS3. The serial section and the stain applied has to be separated by an underscore. In this case, P10 and ki67. Then we need a dot followed by the file extension. So let's take a look at this. We can see this is, it's upright, I guess we could say, but if we look at the P10 one, it is upside down relative to the ki67 section. So first I'll showcase what will happen if we try to calculate the alignment without correcting for the this flipped image. So after downloading the Python's the Groovy scripts in this repository, and I'm currently using the most up-to-date ones as of May 17th, 2021. So let's open the script. So the first one we want to do use is calculate transforms. This calculates transformation matrix required to align two images together. What actually gets generated is not an aligned image, rather a 3x3 matrix containing 3 distinct double precision values that contain all the information necessary for saying what kind of transform needs to be applied to an image in order to align it. So all this says is just calculates transformation matrix, but it does not technically align the image. Image alignment only happens at the final stage where we read in the transformation matrices and then apply it to an image. So let's take a look at some of the parameters. We'll leave it as affine. P10 will be our reference state, so we're aligning everything to P10. Whole site image extension is .ndpi. This is commented out, so we don't have to worry about this. Auto-aligned pixel size, the downsampling factor for calculating the transformation matrix. In other words, it'll shrink both of the images by a factor of 30, calculate the transformation matrix, and subsequent image alignment accuracy metrics based on the efficacy of this alignment. Align specific we'll leave for null for now. Skip image, we'll leave it as 0. And let's take a look at some of the experimental features. This only applies to immunofluorescence images if you want to use a specific channel for alignment. This iterations is the number of times to iteratively calculate these alignment parameters or the alignment measurement. So it'll apply an alignment once, and then it'll repeat this process over and over again. So if you guys want to see how this visually looks, you can go to Analyze, Interactive Image Alignment, load up the ki67 image, and we just click Estimate Transform. Yeah, so you can see it transformed slightly even though it's flipped, and I'll explain how to account for this in just a second. Let me apply it again. It moves again, and it'll basically move and move and move over and over again. Now, that alignment did not work, well, because the image was flipped up by 180 degrees. And this is where move rotation comes into play. This is the degree in which the moving image, ki67, or all subsequent serial sections that you want to align, are rotated by clockwise, I believe. So here we specify 180 degrees, and a decrement factor, or decrement factor. Basically, with each subsequent iteration, do you want to increase the resolution at which the transform is calculated. Number of iterations, decrement factor, and autoline pixel size are all different parameters you'll have to play with. There isn't really a set rule as to what to use. And on that note, let's click run. All right, so it's starting off at 30, 88% accuracy. It's using a slightly higher resolution. The accuracy does decrease slightly. Right, how can we improve this? What if we bump it up to 40? $88, $88, $88, $83, $87. So it seems as though decreasing the resolution at which the transformation is calculated decreases the quality of the alignment. But even on that note, an 88% accuracy is 88, 87 is still reasonable. The most important way of evaluating alignment is just seeing how it looks and seeing if the edges of the tissue, if certain structures within the tumor line up. So let's apply the transformation matrix. And over here we have some parameters. So if this is commented out, it's not going to write out an image. What it'll actually do is a image server will appear in this project list where you can preview the transformation matrix. I believe this is either, the image is stored either transiently in RAM or in some kind of temporary memoization file. But yeah, if you comment this out, it's not going to write it out. It'll just keep it there for preview. So let's click run. Done. Let's take a look. So we will turn off these channels of P10 and turn off that from Ki-67. And as you can see, it's done a reasonable job in aligning the two images. It's not perfect by any means, but generally did a pretty good job. So now keep in mind, if you're not satisfied with this alignment, there are also options to do manual alignments, and I'll explain how those work in just a sec. So let's open our static image and delete our preview. And open up the manual alignment script. So what this does is essentially allows you to save a transformation generated through this interactive image alignment script or overlay. So we've loaded an image. First thing we want to do is rotate it by 180. Great, it's flipped. I'm going to adjust opacity. All right, it seems like we want to rotate the Ki-67 couple of degrees to the right. So let's one. Oops. There we go. All right, not too bad. You can hold the shift key down, move it up, and now that we have a rough alignment going on, we can click Estimate Transform, and a little better. Let's decrease this to 10. Estimate Transform again. With higher resolutions, they'll take slightly longer. You also want to make sure you have sufficient computational resources for calculating transformation matrices at a higher resolution. So around 32 gigabytes of RAM, and I would like a medium to high-end processor. All right, seems like it's done. Okay, not bad. Now, of course, you're still encountering the same issues with as in before. It's not a perfect alignment. But this is as good of an alignment. I would confidently say this is as good as an alignment as we would get using affine or rigid-based transforms. The discrepancy you see here is the result of local deformations, and that might require deformable image registration techniques that are not available within Qupath, but do exist in some of the more recent publications. Other histology platforms such as Visiofarm. There's a MATLAB script I'm working for that does deformable image registration on a GPU. And I think someone wrote a plugin for IC or something that'll do this. Anyways, if we're satisfied with this alignment, let's take a look and see what it says here. Open it here. While the overlay is still open, set name to name the current moving image and run script. What is the current moving image? OS3, well, it's this. We can rename, copy, name here. And click run. Perfect. It captures the transformation matrix present here. So if we look at the project file, this is our transformation matrix. It's not an NDPI image, it's just a 3x3 matrix with NDPI extension. Now going back to apply transforms, we click run to get a preview of how it turns out. We switch off some of the channels. Let's say red, green, and blue. And you can see it does, the manual alignment seems to do a somewhat better job. Generally speaking, in all cases, manual alignment would give a better output. The purpose of using this automatic calculate transform steps is if you're working with large data sets. Let's say you have 7 tumors with 4 serial sections from each. Maybe you'd want to do a first run through using this automatic alignment transformation, evaluate the alignment for each of the sections, and if some of the sections need to be manually aligned, then you can use the manual alignment through the interactive image alignment plugin. And yeah, so now that we're satisfied with the image, we can write it out. So using the same script, all we have to do is uncomment this line, which enables writing out the image as an OME TIFF. Well, actually, before I do that, let's take a look at stain deconvolution. These channels over here, you can see are red, green, blue, but let's say we have a brown chromogen that we want to isolate from each of them. How can we do this? Well, let's delete this image. We set perform deconvolution to true, and we click run. Now what's important to note is only run apply transforms on reference images. In this case, P10 is our reference stain. It'll give you an error if you try to run it on something else. And make sure there aren't any other files cluttering up this thing, because it might get confused. So let's save, run. Perfect. Now we have a fairly interesting looking picture. What we have here is basically an overlay of all of the different deconvolved stains using the predefined DAB color vectors. I'd strongly recommend setting your color vectors ahead of time by going to Analyze, Preprocessing, Estimate Stain Vectors, and all of this stuff is outlined in the Qupath tutorial documents. But let's take a look at the DAB stain of the P10 and the DAB stain of the K67. Let's make this cyan, and let's make this red. The K67 seems a bit dim, but we can add that. The reason being is because of all of this white space. It's affecting how the stain is actually normalized from a purely visual standpoint. I'm sure if we crank up the max display settings, it'll improve the K67 staining inside. Oh, I'm doing it for the wrong stain. There we go. And these lines are just visual artifacts with the scanner, nothing to do about them. All right. Just make sure normalization is correct. This looks reasonable. And uncheck show grayscale. Perfect. So any points that are white means you have an overlap between P10 and K67. Like here, for example. This is an example of a K67 positive P10 negative cell. This is an example of a P10 positive K67 negative cell. And yeah, this is one example of how you can use serial sections of a brown stain to perform multiplex immunohistochemistry. What's important to note, however, is that these are serial sections. You're essentially sampling two different populations of cells. The cells present on one slice are certainly not going to be the exact same cells present on the subsequent slice. The only time you want to do this kind of alignment for dab stain sections is if you have a regional marker. So it seems like P10 in this case regionally delineates a broad area, which presumably wouldn't differ if you go to the adjacent serial section. Markers of hypoxia are another example of regional stains. Cytokeratin stains are another example. And yeah. So we can close this. And now we can write out, let's just write out a normal red, green, blue channel image. Pull this out, perform deconvolution to false, uncomment the output, save, and we run. So we can view the progress of it being written out here. And the alignment or the aligned image should end up getting written in the project space directory unless you specified the path otherwise. All right, so when I was trying to write out the image at the original resolution, in other words, output downsample was set to 1, I was getting a file size that was over 17 gigabytes, despite the two inputs only being 2 gigabytes in total. I'm not sure what the reason is. Could be a compression artifact, could be something involving pyramids, could be both. But for the sake of the demonstration, we'll set output downsample to 10. And so we ran it, and we now have an image written out. Our image is this. Now we can take this OME-TIFF, load it into Qupath to see if it reads. Want to make sure I'm recording. Yep. Let's set the image type to other, doesn't really matter. And voila, we now have the aligned and appended image. Now, unfortunately, the channel name does get lost. But if you know the order at which you align the images in, it shouldn't be a problem. Plus, you can always, visually inspect it. But yeah, we can see the alignment before and after. I believe the first three are probably going to be P10. Yep, P10. And then the last three are K67. And yeah, this is an example of the image alignment script. Does a reasonable job. I've used it for a lot of my projects, and I've never had an issue with any of the outputs. Keep in mind, if you do want to write out an image in its original resolution, you probably wouldn't want to work with an image of this size. It's about 12,000 pixels long. Quite a lot of data. Yeah, so I think that's that. If you have any questions, open up a new issue in the GitHub repository, and I'll try and answer it as soon as I can. But yeah, I hope this tool, serves its purpose for you or your colleagues or anyone else who's interested in whole slide image alignment. Thanks.